and welcome to this introduction to discrete calculus. In the two videos following this one, I'm going to go through how one would go about differentiating and also integrating a function on a computer. But before we get there, we need to do some basic stuff. Handling mathematical functions on a computer is not entirely straightforward. Think about it this way. A function really contains an infinite amount of information, while a computer is only able to store finite amounts of data. Physical quantities such as temperature or density or velocity, they are usually defined as continuous functions of both space and time. And one can introduce discrete versions of such functions, which will be more convenient on a computer. And I will try to illustrate how you do this with a few examples very soon. What we do is that we introduce a set of coordinates, discrete coordinates x, and store corresponding values of the function in an array. And then we use some sort of plotting tool which will plot a straight line between all the function values. So a discrete representation of a continuous function would be, from a programming point of view, nothing but a finite set of coordinates and corresponding function values in an array. So suppose we want to generate a plot of the sine function as a function of x, where x can take values from 0 to 2 times pi. Alright? So what we do is we define a set of x values and an associated set of values for the sine function. So more precisely, we have some x's defined as I times h, where I is simply an integer from 0 and all the way up to some number n, and age is what we call the step length, which would be 2 pi divided by the number of values. And now the associated function values of the sine function would be s of I equal to the value of the sine function for all these xi values, where again I is from 0 and all the way up to some number n. Mathematically, what we have is a sequence of points xi and si, from where I goes from 0 and all the way up to n. So the x coordinates constitute a mesh or a grid, and each point that we pick on this grid is called a node. So the discrete representation of the sine function from 0 to 2 pi would consist of this mesh of x values and also the values of the sine functions at these nodes. And the parameter n is usually referred to as the mesh resolution. So if we have a high n, we have many points, we have a high resolution. And now I'd like to illustrate this in a short program in Python. First, some imports. We'll import numpy as, or numerical Python as np, and we need to import a plotting tool. I'm going to use pyplot from matplotlib. Alright, and we are going to make our little script here take in a command line argument for our n, the resolution of our mesh. It's going to be an integer. So that's argv, and that will be the first argument, and because we need access to our system, so let's import sys. Import sys, there we go. And we also need to define our x, which is going to be the number of points, or the number of points in our mesh will be decided by this n. So this is going to be linspace from 0 to 2 times pi and n plus 1 point, so we'll be sure that there's n of them. Alright, and then our function values, which is the sine function at these x values. And now we'll plot it. we will plot our x points and our function values, and we will label this as our n values. So we'll have n equal to n, like so. And this will show up if we add a legend. And then let's show this, shall we? Okay, and then we need to open a terminal to try to call this function and see if it works. Alright, so let's first try to call it without any input arguments. We see we get an error because it needs a number. So let's first start with a low number, 5. Okay, here we go. We see that we have some sine function like stuff, but because we have so few points, it's very jagged, very erratic. So let's try to increase it to 10. And you see that it gets better, and it will continue to get better if we keep increasing our number of nodes. There we go. That's very nice. But we could do, let's do 1,000. And there you see, almost perfect. So this is the first example of how to represent a function on a computer. This is with 100 nodes, sorry. Now suppose that we already have a discrete version of the sine function, as we do, because we already wrote it on the computer. What if we want some information about the function between the nodes? We already we have exact values at the nodes, but what if we want information of the function between the nodes? And finding function values between the nodes in a discrete function is called interpolation, which you might have heard of. Alternatively, we can say that we are interpolating a discrete function. You could do an interpolation graphically by simply looking at the graph, a plot of the function. As we did in our program, we drew a straight line between the points. So then you could simply look at the x and see what is the value, and you would do a linear approximation or a straight line approximation of the function, of the underlying continuous function. A mathematically precise description of the same procedure is the following. So assume that you have some value x, and x is somewhere between xk and so this is somewhere in between xk and xk plus 1. So these values, the two x's here, they are nodes in your discrete function representation. So we have some linear function passing through these 2 points, one at xk, sk, and to the point xk plus 1, sk plus 1, right? That makes sense. The linear function that passes through these 2 points, this is typical high school mathematics really, would be something like this. So let's write a capital S for the k. It's a function of x. You will start at this value, and then you have a fraction xk plus 1 minus sk divided by xk plus 1 minus xk. So this would be the incline. And then a typical x value minus xk. I think this should be fairly familiar. So this expression here would provide a true value of a function at the nodes at xk plus 1 and xk, but it would provide a linear approximation between the nodes, which is a fairly good estimate in most cases, especially if you have a high resolution in your mesh. So we say that s of kx will interpolate the discrete function on the chosen interval. And now to some programming again. Alright, so now we will try to make a script that interpolates a function, and then we will see how good the function fits, or how good the interpolation is. So first we need the usual stuff. We need numpy. Whoops. Import numpy as np, and we also need plotting library, pyplot splt, and we need sys again because we want to do a similar thing as before. We want to have two command line arguments now: the number of points in our function, discrete function representation, or the number of nodes, the mesh resolution, and we also want the x where we are starting our interpolation, right? So we call this xp, which is our point. It is not necessarily an integer, so we'll just use the eval function. And we'll take this as the first argument, right? Yeah, that's it. And then our n, which will be an integer, and that will be the second argument. And then we'll define our interpolation function as a function in Python, s of k of x. This is the function that we just wrote, so and I can just go straight to return, and we will define a sign function shortly. It will be this lowercase s, so don't get confused on me there now, don't do it. Plus, and I think we will be out of space soon, so I'm using the backslash to get our new line. So what do we have? We have s, and we have k plus 1 minus s of k. Yeah, and we divide that by our x of k plus 1 minus x of k, and we multiply the entire thing by xp, which is the point, minus x of k. Alright, so x of p is the point we're supposed to evaluate it, and we need a step size, and we want to do this all the way to 2 pi, so that will be 2 times pi divided by n, which is the resolution, and x is still just a linear grid or mesh from 0 to 2 times pi to n plus 1, and s is sine of x, right? And k will be some integer, xp divided by age. So this will actually be a point on a value that we already have, right? So these s's here will actually, it will pick out the correct value in our function, and we want to print something, an approximation of sign, and this will be the point we put in, xp. We should print the value from our function, sk of k. Alright, yeah. And we also want to print the exact value of sign of xp. That one as well, which will be, yeah, then we'll just simply use, oh, I forgot my numpy namespace, there you go. Here as well, of xp. I think that will be correct, yep. And lastly, we'll print the error, which will simply be sign of xp minus the sk function of k. Okay, and we actually do not need a plotting tool for this. So let's try it out by going to our terminal. We write Python discrete 1a, that's our program, and we want to evaluate this at something difficult, so we'll pick the square root of 2, and let's pick 5 values. and see how it goes. An error. Okay, I think we need to simply make this a string, like so. Let's go. And then we have an error again. I wrote a carré instead of an asterisk. There. Third time's the charm. No. Again, I forgot my namespace. There we go. Fourth. And then here we get a type of object that our integer is not subscriptable. And does that make sense? Oh yeah, I see. This input argument should be the k value. Sorry about that. There we go. And then we get the approximation of sign at the square root of 2. And we also get the exact value, and we see that we have an error. And this error should decrease if we increase our resolution. Yeah, there we go. That's a little bit better. 0.036, and there it's 0.0822. Let's try an even larger value at 100. And there we see that our error gets smaller and smaller and smaller. Yeah, as we would expect. So in general, we can create a discrete function of a continuous function as follows. Say we have f of x on the interval from a to b. We define the distance between the nodes as h, so this is the step size kind of, which would be b minus a divided by n, which is the resolution. So n is any integer, well, hopefully larger than 0, but anyway, all the way up to, yeah. So at the nodes, x would have the following value. xi would be the starting point plus I times the step size. And I would be 0, 1, and so on, all the way up to n. Actually, we should rewrite this so that this makes more sense. And the discretized function, or the discrete version of the continuous function f of x would now be, let's call them y of I equal to the function value at these points. It's as simple as that, and you would get a set of points xi, yi from I equal to 0 and all the way up to n. And that's it. See you in the next video.